Episode 2, Number Theory. The title of my study is Special Divisibility in the Product of Perfect and Fibonacci Numbers. Hi, I'm Pythagoras. During my time, Pythagoreans produced a theory of numbers comprised of numerology and scientific speculation. In their numerology, even numbers were feminine and odd numbers masculine. The numbers also represented abstract concepts such as 1 stood for reason, 2 stood for opinion, 3 stood for harmony, 4 stood for justice, and so on. Their Arithmetica had a theory of special classes of numbers. There were perfect numbers of two kinds. The first kind included only 10, which was basic to the decimal system, and the sum of the first four numbers, 1 plus 2 plus 3 plus 4, which is equal to 10. The second kind of perfect numbers were those equal to the sum of their proper divisors. A perfect number is a positive integer that is equal to the sum of its divisors. However, for the case of a perfect number, the number itself is not included in the sum. The Greeks called a number such as 6 or 28 a perfect number because the sum of the proper divisors in each case is equal to the sum or to the number. The proper divisors of 6 are 1, 2, and 3, and their sum is 6. Although perfect numbers are regarded as arithmetical curiosities, their study has helped to develop the theory of numbers. Euclid proved that a number n of the form 2 to the power of n minus 1 times 2 to the n minus 1 power is a perfect number if the factor 2 to the n minus 1 is prime. For example, if n assumes the value 2, 3, 5, or 7, the expression 2 to the n minus 1 takes on the value 3, 7, 31, or 127, all of which are prime. For these values of n, we obtain the perfect numbers 6, 28, 496, and 8128. The Neoplatonists Nicomachus of Gerasa and Iamblichus of Chalcis listed these perfect numbers and concluded that they follow a pattern. They alternately end in a 6 or an 8. And there is one perfect number for each interval from 1 to 10, 10 to 100, 100 to 1000, and 1000 to 10,000. They conjectured that both parts of the pattern would continue, but in this they were wrong. The fifth perfect number, which was discovered in the 5th century, corresponds to n equals 13 and is 33,550,336 with 8 digits rather than 6. In addition, the 6th perfect number, like the 5th, ends with a 6th. In 1961, the 20th perfect number was found. It contains 2,663 digits in the decimal representation and corresponds to the case where n is equal to 4,423. Today, 37 perfect numbers are known. The prime for the largest of these is 2 to the power of 3,021,377, which is 909,526 digits in length, and the largest perfect number is 1,819,050 digits in length. It is not known whether there are infinite numbers of perfect numbers. In 1757, Leonhard Euler probed that every even perfect number must be of Euclid's form. It has also been proven that every even perfect number must end in 6 or 8, and if it ends in 6, the digit preceding it must be an odd. No one has yet discovered an odd perfect number, but it is known that none exist below 10 to the 20th power. With all those findings, will I still have the opportunity to find something interesting with the numbers or the perfect numbers? Hence, this paper aims to explore more the perfect numbers, generate some conjectures, and prove them. For our preliminary concepts, we have known that perfect numbers is a positive integer that is equal to the sum of its proper divisors. The smallest perfect number is 6, which is the sum of 1, 2, and 3. Other perfect numbers are 28, 496, and 8128. On the other hand, Fibonacci numbers are numbers taken from the Fibonacci sequence, which is a series of numbers, and that number is the addition of the last two numbers starting with 0 and 1. The Fibonacci sequence are 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, and 55. And it continues as you add the last two numbers together. With that curiosity in mind, this paper seeks to answer the following questions. First, what special feature can be drawn from the prime factors of different perfect numbers between 1 and 100 billion? Is the product of a perfect number and a Fibonacci number, when both arranged or sequenced, divisible by 4? The third, is the product of a perfect number and a square of a Fibonacci number, both arranged by sequence, still divisible by 4? Fourth, is the product of a perfect number and the cube of a Fibonacci number, both arranged by sequence, still divisible by 4? And lastly, is the product of a perfect number and the nth power of a Fibonacci number, when both arranged by sequence, divisible by 4? After thorough investigations and observations, I came up with the following results and discussion. For the first question, what special feature can be drawn from the prime factors of different perfect numbers between 1 and 100 billion? This table shows the list of prime factors of every perfect number from 1 or between 1 and 100 billion. For 6, we have 1, 2, and 3. For 28, we have 1, 2, and 7. But then our 2 here in a second power. For 496, we have 1, 2, and 31 with 2 to the 4th power. As it continues with 8128 with 1, 2, and 127 with 2 has a 6th power. And it continues, and if you can observe, there is a special observation that you could do with the following result. In my study, the table above shows the list of prime factors of every perfect number, which entails that aside from the divisibility of 2, which is according to the background of the study, is not yet proven except for 10 to the power of 2 and 20. They are all divisible by 4 except with the first number 6. Going back to the table, for number 28, the 2 to the 2nd power implies that it is divisible by 4. For 496, the 2 to the power of 4 can be factored out by 2 to the power of 2, 2 to the power of 2, or multiplied by 2 to the power of 2. Therefore, it is also divisible by 4. Same with 8128, factoring out 2 to the power of 2 times 2 to the power of 4 implies that it is also divisible by 4. Same goes with 33,550,336 and so on with the other perfect numbers, reaching the 1, 3, 7, 4, 3, 8, 6, 9, 1, 3, 2, 8, which is a perfect number below 100 billion. The second question is, the product of a perfect number and a Fibonacci number, is it divisible by 4 when both arranged by sequence? Table 2 shows the product of every perfect number and Fibonacci number, and a column that shows whether or not the product is divisible by 4, and the residue and the modulo in modulo 4. It can be seen that for the first power of every Fibonacci number, when multiplied to every perfect number, gives a product that is divisible by 4. If you can see, 6 multiplied to 0 is equal to 0, which is divisible by 4. 28 times 1 is 28, which is divisible by 4, that gives a quotient of 7. Same goes with 496 multiplied by 1, which gives us a quotient of 124, and so on. So the residue for every number when the perfect number multiplied to a Fibonacci number gives a residue of 0. In the next table, it shows the prime factors of both perfect and Fibonacci numbers. This actually proves that why is it divisible by 4. If you can see, for number 1, it is already a 0, so it's really any 0 is divisible by number 4. For number 2, so same as what the previous table presented in terms of the prime factors of our perfect numbers, it really shows that 2 to the power of 4 is actually 2 to the power of 2 is divisible by 4. 496 has one of its factors as 2 to the second power, which implies that it is also divisible by 4. Same goes with number 4, fourth perfect number, the fifth perfect number, the sixth and the seventh. Hence, this table proves that every product of perfect number and Fibonacci number results to a product that is divisible by 4. For question number 3, is the product of a perfect number and the square of a Fibonacci number when both arranged by sequence still divisible by 4? Table 4 shows the product of every perfect number and Fibonacci number, and a column that shows whether or not the product is divisible by 4 and the residue in modulo 4. It can be seen that for the second power of every Fibonacci number, when multiplied to every perfect number, it gives a product that is divisible by 4. That is because every Fibonacci number after the 0, when squared and multiplied to the perfect number corresponding to it, doesn't affect the product, because in the first place, the perfect number 28 going down is already divisible by 4. Hence, even if we square every Fibonacci number, we still arrive with a product that is divisible by 4. For our fourth question, is the product of a perfect number and cube of a Fibonacci number when both arranged by sequence still divisible by 4? Same argument with our third question, which is, even if we cube every Fibonacci number when multiplied to our perfect numbers correspondingly, it still gives a number that is divisible by 4, because in the first place, the second until the seventh perfect numbers are already divisible by 4. This answers our fifth question. Is the product of a perfect number and the nth power of a Fibonacci number when both arranged by sequence divisible by 4? So we answered the question. Even if we multiply how many times our Fibonacci number, we will still arrive with a number that is divisible by 4, because the second to the seventh perfect number, we have already proven that they are already divisible by 4, and when multiplied to any number result to a number that is still divisible by 4. With this, we came up with the following conclusions. The first one, it can be concluded that aside from the fact that every perfect number is divisible by 2, every perfect number is also divisible by 4 except for the first one, which is 6. Second, when a perfect number is multiplied to every Fibonacci number, both arranged by sequence, results to a number divisible by 4. Lastly, when every Fibonacci number is raised to whatever n number, which n is any number is an element of any natural numbers, the product still gives us a number which is divisible by 4. With that, it concludes our study that is entitled Special Divisibility in the Product of Perfect and Fibonacci Numbers. Thank you very much.